So in the next two lectures, I'd like to talk about structure loads. And element loads, okay? And here we are on page 3.1 of the reader, right? And for this one, again, I want to remind you the very first example that we did, right? We had a ceiling here, and we had a rope or a cable suspended from the ceiling, okay? And that cable had a distribution of gravity load, right? G, gravitational acceleration, force m times g, right? Pointing this way, okay? And so the deformation of this cable will be caused by an application of a distributed gravity load, okay? And that gravity load, as you can see, right, is distributed in a constant fashion and points along the element length, okay? And so far, we covered situations where you had a structure, you could assemble its stiffness matrix, right? And we only know what to do when the structure is subjected to either direct applied sort of nodal forces, right, and displacements at nodes, okay? And so what I want to discuss are element loads, okay? And these could include, as I said, gravity, okay? Again, if you're looking at maybe a model of a house, and then you have a bunch of snow, right, sitting on the roof, right, you can see that this snow will sort of have gravity will act downward, right, due to snow, and some of that will have a component that's tangential and then a component that's vertical, okay? So for truss elements, we're only going to be considering tangential components going forward, okay? And then we'll show you when we start introducing more complicated elements, like beam column, right, it'll be bending, and it's precisely the bending part of the equation that will be able to handle transverse loading, okay? Right, and so the modeling paradigm, right, is as follows, okay? So supposedly you have a structural member, looks like this, okay? And we're going to put this guy on pins, right? Remember, this was a node I, this is a node J, right? X-axis goes this way, okay? Element has property EAL, right? But in addition, we'll subject it to a distributed force, okay? The force doesn't have to be constant, okay? So it's pointing in the direction of the element, right? So again, we're in the local coordinate system. Okay. But the magnitude of that force at every point along X, okay, can change. Okay. And so now, consider a situation like this, right? Both ends are pinned, okay? So there's not going to be any motion of the nodes. All right. However, the application of this force, right, will result in sort of end node forces. Okay. So what do I mean by this? Right. So if we do an expanded view, right, this is our node I, this is our element, this is our prescribed load, okay? This is a force distribution, okay? This is a node J, okay? All right. Then, this distributed load, right, will cause end node forces, okay? And these end node forces I'm going to denote by F's, okay, right? Prime, because it's in a local coordinate system, and F, okay, because they don't come from end node displacements, but they come from a distributed load, some kind of equivalent nodal force that results from an application of a distributed load. Think of it this way, okay? And those you'll have acting in all directions, right? So this node, you're going to have f prime 1 going this way, right? F prime f2, okay, going this way, right? Because there's no vertical load, this is 0 a priori, right? Load. Okay, the truss element doesn't know how to take a vertical load. Okay, that's the point. Right? And on this end, you have f prime f3, right? And f prime f4, again, because there's no vertical load, this guy equals to 0. Okay. Right? And of course, there'll be support reactions because of the application of that force, and these support reactions are equal and opposite, right? F prime F1, F prime F2, right? F prime F3, and F prime F4, like this, okay? And so basically, without the nodes moving, without any deformation, right? The application of a distributed force, right, results in, right, this f prime f vector, right? Vector of end node forces due to the applied distributed load, okay? And so, of course, as you change the load, the end forces will change as well, okay? And so now, let's have a combination of the two, okay? So supposedly you have this element, we'll put node I here, right? Put this guy on a pin, okay? Put this guy on a roller, this is J. And then I have a distributed load like this. Right. So now the element is free to move as well, okay? And so in this case, right, the picture for the element looks like this, okay? So if I'm interested in the end node forces, F prime, okay, then those will come from two contributions, okay? F prime F, okay, which comes from a distributed load, okay? And then I have a component that comes from the multiplication, right, of K prime times delta prime, okay? Distributed load, and this comes from the motion of end nodes. Right, the question you may ask, why additive? Meaning, you know, why do you add the two things together and not do anything else, right? Well, this goes back to the differential equation, okay? Right? Your differential equation, if you recall, is this, d dx, right, EA du dx, okay, equals to minus w of x, okay? And so then you can take this equation, right, and you can come up with a solution u1, okay, which satisfies d dx EA du dx, right, equals to 0, and then u at 0 equals to some u0, u at L equals to some ul, right, purely driven by displacement boundary condition, right? And then you can come up with a solution where you have d dx EA du dx equals to minus w, okay, where you set 0 boundary conditions. U0 equals to 0, right, u of L equals to 0. Okay? And so clearly, right, you have a situation like this, right, where you do have the right-hand side, and you do have the boundary conditions, and the total u would equal U1 plus U2, right? And then if we talk about the force distribution, right, then the total force would be what? EA du dx, okay? That would equal to EA du1 dx plus EA du2 dx, okay? And so this is sort of analogous to K prime delta prime, right? And this term would be analogous to the F prime F, okay? So to answer the question why additive, right, is because the underlying differential equation is linear, okay? And thus is subject to what's called a superposition principle. So if U1 satisfies and U2 satisfies, then the sum of the two satisfies the equation too. Of course, you have to carefully sort out the loading and the boundary conditions. Okay. All right. And so at the structural level, right, at the element level, then all you need to do is take your F prime, right, and you know, have the term that you had before, right? F prime equals kappa prime delta prime, right? And all you need to do is basically come up with a vector F prime F that you can add to your system, okay? And so then from there, you're going to go to the global coordinate system, okay? The local, still element, right? Then next step is the element global. Okay? Where you replace F prime with F, K prime with K, delta prime with delta, right? Plus FF. Okay? And we'll show you how to come up with that, right? And then from there, okay, you scale up to the structure level. Okay, where you say PF, right, is what? Is KFF, UF, right, plus some P0. Okay. And so this part, right, kind of going from here to here to here remains the same, right? And you just need to track down the evolution of F prime that starts in the local system, gets converted to the element global system, and then gets converted to the structure level. You see? And so then the way you come up with your displacement solution, right, is you take KFF, you invert this, and you multiply now by the difference between PF and minus P0, like this. Okay. Right. And so this is how your distributed loading makes it all the way to the structure level and how it affects the final structural solution. Okay. So a fairly simple concept. Okay, so next, let's do an example. Okay, so now, you know, in most cases you can do simple loads, like constant or linear, right? So let's look at the case of a uniformly distributed load. Distributed load, okay? And so now here's your element. Okay. IJ, right? Decided that we're going to put it on pins, right? We don't care how the end nodes move. I'm interested specifically in the response based on the application of a constant load now, right? So let's identify its magnitude to be constant and acting in the positive x direction. So when W is positive, we assume it's acting in the positive x direction. So this is Wx of x, and it equals to W, and it equals to a constant. Okay. So unfortunately, if you change the load, you have to redo the calculation. EAL, right? So in the software, what you see is you have some pre-programmed load distributions. Okay. Right, and let's go through the motions. So differential equation, right, that governs the problem is EA, and assume prismatic again, d squared u dx squared equals to minus w. Right? Right, this is the value of the constant load. U at x equals to 0 equals 0. U at x equals to L equals 0 too. Okay, so this is our boundary value problem that we need to solve. Okay, remember our general solution is u of x equals to, right, u homogeneous, right, of x plus u particular of x. Right? So then u homogeneous is a solution that satisfies the right-hand side of the operator to be 0, right, with arbitrary boundary conditions. We derived this before, and this just becomes C1 plus C2x, okay? And then the particular solution, right? Again, you need to kind of do it by inspection, right? So you can go ahead and divide through by EA, like this, okay? And then you need to find u such that its second derivative equals to a constant, and the constant is minus w over EA, okay? And then you get here minus w over 2 EA x squared. Okay, so you take first derivatives, the 2's cancel out. You take a second derivative, you're left with minus WEA. Okay. So next is you apply BCs to determine C1 and C2. Okay. And if you carry out the calculation, right, you will find that at the end of the day, your UX equals to, okay, WL over 2EA times X minus W over 2EA times X squared. Okay, so all the dimensions are correct. Notice quadratic distribution of the displacement. Okay. So another way to write this is u of x is, to simplify, right, w over 2EA x L minus x. Good, right? However, so if you were to plot this, okay, you know that you're going to be 0 here, you're going to be 0 there, okay, and you get a parabolic profile in between, right? That looks like this. And so if you go ahead and evaluate the solution here, right, you get W over 2EA, right? And this gives you L over 2, the first X, and this gives you another L over 2. Okay, which is W L squared over 8 EA. Okay, so this is by how much the midpoint of the bar displaces, and then that displacement quadratically goes to 0 at the ends of the bar. Okay. Well, what's important here is not so much the displacement, right, but the normal force. That's the next thing we need. So if subjected to that load, right, the normal force is EA du dx, right? And if you carry out the math, right? You substitute the displacement from before, you get W over 2, okay, L minus 2x, okay? So note, right, distribution is linear. Okay, so no longer constant, right? So you can't say whether your element is in tension or in compression, right? You can ask that question, and the answer is it depends where you sample the force. Okay? Then it's very important that this course is starting to introduce, quantities that have continuous distribution, right, of your solid or of your structure, and this is how a lot of the analysis is carried out. Okay. Right. So if we were to go and take the element, right, if we were to plot this function from 0 to L, right, smack in the middle, for x equals L over 2, you get a 0, okay? At 0, you get a L, right? You get WL over 2, right? So put a point here. At L, right, you get minus WL over 2, okay? So this becomes a distribution of your force. Positive, crosses 0, negative, okay? Right, so positive, this guy is in tension. Okay, tension. Once it crosses there, it goes into compression. Okay? And then, you go to this edge, to the left edge, your tensile force reaches WL over 2, right? You go to the right edge, your compressive force reaches WL over 2. Okay? So then what's F prime F? Right? Well, you can see it directly in the plot, right? Follow the arrow, right, here, and go all the way to the node, right? So you find that this guy, right, on the left edge, points to the left and has magnitude WL over 2. Okay? You go to the right edge, right, follow this arrow, it's in compression, right? So you go to the right edge, you evaluate, you get another force that points to the left with magnitude WL over 2. Okay? So then you just go and record this in a vector F prime F, right? So this is exactly F prime F1, right? Then F prime F2, there's no vertical action, is 0, right? This becomes F prime F3, right? And then in the vertical direction, F prime F4 is 0. Okay? So you just populate the vector based on your solution. You get minus WL over 2, 0, minus WL over 2, 0. Okay? And again, you can do a sanity check, right? You can think of this bar, where you go and you apply load like this, okay? Constant load, W, right? Spread over a distance L. So what is the total force, right? W times L, okay? Now, this bar is fixed, it's not going anywhere, okay? So you need end node forces, right, that would go and would oppose that load, okay? And that's exactly what you see here, okay? Half of this load makes it into the first part of the vector, right? And the other half of that load ends up there. So these two loads of WL over 2, right, are resisting the corresponding constant load of W spread over the distance L. Okay. Good. All right. All right. So where do you go from here? Right? So you start with F prime F. Okay. And so this is what F prime F looks like for a constant load. I mean, you can check what happens with other load shapes, like linear. Okay. Right. As a next step, okay, you go to the global coordinate system, F. Okay. Right. It's how the forces related between the local and global coordinate system through the rotation matrix. So this is exactly gamma, right, matrix, ROT, transpose, right, times F prime F. Okay. So you use the same rotation matrix as you do for the conversion of the stiffness matrices, you do it for the F prime. Okay. And from there, you go to PF0, structure level, right? What does that look like? Okay. Using the formal expression and Boolean matrices, you get E equals 1, right, to NEL. For every element, you grab its Boolean matrix associated with 3 degrees of freedom. You put a transpose, right? And then from every element that it has a distributed force in it, right, you grab the corresponding force vector, right, which is obtained by rotating the local guy, okay, like this. Okay, you want to do it this way, right? Or PF0, you can obtain it using direct assembly with ID arrays. Okay, and that's what you do in the code. Okay. Right. So as in the beginning of the lecture, you end up with a linear system that looks like this: KFF, UF, right? I'm presenting it in the reduced format. Same applies for the full format. PF minus PF0. Okay, so this is how your right-hand side of the equation is modified. Okay. From there, you solve for UF, KFF minus 1, PF minus PF0. Okay. All right, and then you go through element state determination. Okay, and so this is where it gets a little bit interesting. Okay, so what are the steps, right? You take your UF, global vector, right? And then you would use the ID array for element E to extract the displacement vector, right? Delta E, like this. Okay? Right? Nothing changes, same as before, right? Now that you have your displacement vector in the global coordinates, right, you get this in the local coordinates. For every element, you get delta prime E equals to gamma ROT, right? Depends on the element, in element geometry, times delta E, like this. Okay? Right, and now that you have delta prime, okay, you get the end node forces in the prime coordinate system, right, as K prime E delta prime for element E, plus you add whatever it is that comes from the distributed load. Okay, so that's the new guy, F prime E. Okay, so this is as before, and this is new. Okay, right. So note here, right, that what we would do in the past, okay, is we would obtain delta prime E, right, and then we would get the delta prime over bar E, basic displacement. Okay, but the basic displacement here is more problematic because the applied forces, right, due to distributed load, don't make sense, right, in the basic displacement. Okay. Right, remember, you can actually relate right? There's the gamma RBM transpose, okay? And the gamma RBM transpose looks like this. 1, 0, minus 1, 0. Okay? And so if you want, right, to get F over bar prime, basic force, right, you would take gamma RBM transpose and you would multiply the F prime. Okay? Right? Then you can take this, right, write down K prime, delta prime, right? This is for element E as before, right? Plus gamma RBM transpose times F prime F E, okay? And so, you know, if this is a constant load, right, this guy was minus WL over 2, 0 minus WL over 2, 0, okay? And if you apply gamma RBM transpose, okay, you get exactly 0, you see? So you do have element end nodes, right? But there is no force in the basic system, right? And you can see it's related to the fact that, right, the force is distributed like this, okay? So you have a tension region, you have a compression region, but on average, the force is 0, okay? And because on average is 0, it doesn't get picked up in the basic system, okay? So the thing to, right? So basically you get no basic system counterpart for F prime F, okay? That is, that's meaningful in any way. Okay, so let's quickly go through the example, okay? The example is presented on page 36 of the notes, okay? And so imagine our old geometry, right? Okay. This is node 2, node 1, okay, node 3, right? This is my direction. This was our element A, remember? This was our element B, okay? The dimensions were 6 and 8. And 8, okay? And then let's go ahead and, right, element orientations were like this, right? And so then let's go ahead and apply a distributed force, right, that's going along the element axis and points from node 1 to node 3, right? And let's say W equals to 3 here, okay? This problem is given numerically, but assume just in the appropriate units, that would be units of force per length, okay, of the bar, okay? So then, right, F prime F for element A is 0. There's no distributed load, okay? F prime F for element B, okay, right, is what? Minus WL over 2, 0 minus WL over 2, 0, okay? What is W, right? If this is the element orientation, W is pointing against the element orientation, right? So we need to take it as minus 3, right? We need to take this guy as minus, apologize, WL over 2. We take this guy as minus 3, okay? And then L was 10 in our units, right? So then the vector looks like this, 15, 0, 15, 0, okay? We do the rotation to the global coordinate system, right? ff for element B, okay, becomes rotation matrix for element B transpose times f prime f element B, okay. Right. If you recall the rotation matrix we computed before, you get 0.8 minus 0.6, 0.6, 0.8, 0, 0, 0, 0, 0, 0, 0, 0, 0.8 minus 0.6, 0.6, 0.8, okay, times 15, 0, 15, 0. Okay. Right, and we end up with the following fully populated vector, 12, 9, 12, 9. Okay. So here are the forces. Right. Okay. Right. So remember, right, in our element, right, this was F1, F, this was F2, F, this was F3, F, right, and this was F4, F, okay? And these, right, were exactly corresponding, right, to U1, P1, right, and U2, P2, okay? So you can see that this entry will go into PF3, sorry, PF1, right, into the structure level, right, first entry for prescribed force, and this entry will go into PF2, okay? All right, the idea array for this element was 0, 0, 1, 2, like this, right? Okay. So what do the equilibrium equations look like, right? I have KFF, UF equals 2 PF, right? And in this case, we assume, right, if you look at the problem statement, we assume that the vertical force is no longer acting on the bar, right? So this is 0, okay? And what remains is PF0. So if we write it out in terms of numbers, 492 for this specific case, 144, 144, 108, U1, U2, okay, what would be the new set of displacements under the prescribed load, right? PF0 was what? F3, F4, what is F3, F4? 12, 9, right? So minus PF0 becomes minus 12 and minus 9, okay? And from here, we solve for U1 and U2 to obtain UF to be 0 minus 1 over 12, okay? So it's interesting, right? If this was the original configuration, right, this node drops by 1 over 12, but doesn't encounter any displacement in the vertical direction, right? So this is going to be your displaced configuration like this. Okay. All right. Good. Okay. So let's do the state determination. Okay. And for this one, again, we'll work element by element. Right? Let's start with element A. Okay. And we compute the displacement, delta A, right, just by looking at the solution. So here, right, 0, 0, this node doesn't move. And there we get 0 minus 1 over 12. 0, 0, 0, minus 1/12. Okay. All right. Because there's no distributed load, okay, I can actually go directly to delta prime over bar, basic displacement. Right? Basic displacement is gamma RBM times gamma ROT for element A, right, times delta A. Okay. I can do the math, right, but you can actually see it. This just ends up being a displacement in X, right? This element is horizontal, so the basic displacement would just be the X displacement component here, which is 0, okay? So I get a 0, and then the element is undeformed and unstressed. Okay? So that's what happens. So basically, that distributed load is taken up directly by the element over which it is applied. Okay. All right, element B. So that's where interesting things start. Right. Again, as usual, I extract delta B. Okay. From the ID array. And again, it becomes 0, 0, U1, U2, or 0, 0, 0, minus 1 over 12. Okay. Right. Now I compute delta prime B, okay, using the application of a rotation matrix, B, okay, times delta B, which I just extracted, okay, and what I find is I get something like this. Equals to 0, 0, okay, the boundary conditions, no surprise, right? This is a restrained node, it cannot move. And minus 0.05 minus 1 over 15, okay? This is my displacement. Okay. Then I compute F prime B, right? Vector of forces in the local coordinate system by taking K prime B, multiplying by delta prime B, right, and adding F prime F for element B, okay? Right. And so what I find here, right, is, remember, the local matrix was like this, 300, 0, minus 300, 0, 0, 0, 0, 0, minus 300, 0, 300, 0, 0, 0, 0, 0, okay? That goes and multiplies 0, 0, minus 0.05, minus 115, okay? And then you add to it what you computed in the beginning, right? 15, 0, 15, 0, okay? And so if you do the calculation, right, you find this. 15, 0, minus 15, 0, right? Coming from the first part, plus 15, 0, 15, 0, okay? And next comes the interpretation. Okay. Right. So what does that mean? Here's your element, okay? Right? And in the local coordinate system, right, this contribution looks like 15 acting this way and 15 acting this way, okay? in the negative direction, right? The element is compressed, right? And the amount of compression is 15 units of force. Okay? This would be the contribution from the end node displacements, right? And then you have this contribution here, okay? Plus zero element, right? And I have two positive 15s, okay? Right? And so we know here, right, that the you have a compression on this side, right? You have tension on that one. Yeah, this is 15. This is 15. Okay? Compression here negative. Tension here positive. Okay? And so now what you do is you combine the constant contribution, right? Compression due to the motion of end nodes, right? With a linear contribution coming from the distributed force. Okay? And if you combine the two plots, right, you get something like this. Negative 15 and negative 15 combine to give you negative 30. Okay? And here, negative 15, positive 15 cancel. Okay, so the forces go to zero there. Okay? And it gives you this final axial force diagram, okay, where you have a state of compression on the entire element. Okay? It starts out with 30 units of force at the base, okay, and linearly decays to zero. Okay? Right. So, right, as you can see, distributed forces contribute to the element state determination in a non-trivial way. Okay. Good. Okay, so let me stop here, and we'll assign some problems that will test these concepts, okay, as part of the homework.